Now let's see the equation of tangent in parametric form. So now that we have discussed about the parametric equation of a parabola, let's see what would be the equation of tangent in parametric form. So let's recap with the parametric representation of a parabola y square equal to 4ax. Suppose I take the parabola y square equal to 4ax. And let P be a point represented by the parametric point T. Now here the parametric point T is referred with AT square and 2AT. So the parametric point T indicates the coordinates are AT square and 2AT, as we all know, which satisfies the parabola y square equals 4ax. So with this parametric point, let's see what is the equation of tangent at this parametric point. If this is the tangent to the parabola, then the equation of tangent in parametric form is given by x minus yt plus at square equal to 0, where t belongs to real numbers, is how we define the equation of tangent at the parametric point t. So equation of tangent at t is given as x minus yt plus at square for the parabola y square minus 4ax equal to 0, is how we understand the equation of tangent in parametric form. In similar manner, if I want to find the equation of normal, let's draw the normal for this parabola y square equal to 4ax. So if I have a normal passing through P, which is perpendicular to the tangent, then equation of the normal at the point P is given by the formula equation of normal at P of t, that is passing through P of t and perpendicular to the tangent, is given by y plus xt equals 2at plus at cube, where t belongs to real numbers. So equation of normal at P of t is n, that is y plus xt is equal to 2at plus at cube, where the parametric point t is at square 2at. T is a real number. Now let's see the concept of number of normals through a given point. So what does this mean? If I take a point in the plane where a parabola exists, then there are totally 3 normals which can be drawn to the parabola from that point. So let's see how we can mathematically support that exactly there are 3 normals at the most which can be drawn from a point to the parabola. Suppose I have a parabola y square equals 4ax. And P is a point out here. Now let me say there's a normal which passes through PE out here. Now we know that the equation of the normal is the normal n is y plus xt is 2at plus at cube. Now let me take a point px1 y1 on the normal. That is, let's say the normal passes through the point x1 y1. If the normal passes through this point a x1 y1, that implies a x1 y1 belongs to the normal, which is equation 1. So if this point lies on 1, that implies it satisfies the equation y1 plus x1t is 2at plus at cube, which on further simplification gives at cube plus 2a minus x1 of t minus y1 equals 0. So this is a cubic equation in t, which is cubic equation in t. Now since this is cubic equation in t, it has 3 roots for t, that is 3 parametric points. That implies there exists 3 roots for this. That implies there exists 3 roots in the sense there exists at the most 3 points, that is all the t's, which are t1, t2 and t3. There exist 3 points. One is t1, one is t2 and one is t3 at the most, which shows that there are normals on the parabola at 3 points t1, t2 and t3. That is, there exists at the most 3 normals from ax1 to the parabola y square equals 4ax. So at the most there are 3 normals from here ax1 y1 to this. One of the normal being n1 and the other normal being n2, that is p of q of t2, and the third normal would be somewhere else. T3, and then this would be the other normal which passes through R T of 3. So there are 3 normals which passes through A. One is normal 1 and the other is normal 2 and the other is the third normal which is out here. So N1, N2 and N3 are the 3 normals which at the most exist for the parabola. So there can be 1 normal, 2 normals or 3 normals from a point to the parabola y square equal to 4ax, because this is a cubic equation in T. Now let's see the number of normals as a criterion or the condition. So coming with the equation of normal, we know that equation of normal is y plus xt is equal to 2at plus at cube. And if px1 y1 or ax1 y1 in the previous case lies on the normal, then we have the condition x1 at cube plus 2a minus x1 of t minus y1 equals 0 is what we get if you substitute the point in the normal. Now this being a cubic equation, we get this with let h equals 2a minus x1 by 3a and g be equal to minus y1 by a is how we take the case. Now with these two values of h and g, we define the number of normals. So with this, we have three cases of with delta, which I define as g squared plus 4h cube. I get three cases through which I define the number of normals as 1, number of normals as 2, or number of normals as 3. So now that I have h equals 2a minus x1 by 3a and g equals minus y1 by a, my delta is given by the formula g squared plus 4h cube, the proof of which is beyond the syllabus on assuming delta. So using delta equal to this, I have if delta is greater than 0, the second case being delta equal to 0 or delta is less than 0. So in this case, number of normals will be 1. So if delta is greater than 0, I get the number of normals to be 1. And if delta is equal to 0, then I get number of normals is 2. And then if my delta is less than 0, I get number of normals is 3. Is how I understand the cases as case 1, case 2 and case 3. Delta greater than 0, there are only one normal. Delta equal to 0, there are two normals passing through ax1, y1. Delta is less than 0, then there are three normals passing through x1, y1 to the parabola y squared equal to 4ax. Is how we understand the three cases. And here, assuming that x1 is not equal to 2a and y1 is not equal to 0, is how we assume in these two cases. And however, it is important to note that x1 equal to 2a and y1 equal to 0 implies number of normals is an exceptional case is equal to 1. Is how we understand the note. So if x1 is equal to 2a and y1 equal to 0, then also the number of normals is 1 as a special case. Criterion for number of normals connected with the delta equal to 0, greater than 0 and less than 0. Now let's see how we can find the point of contact of the tangent. So the topic is about finding the point of contact. With the tangent. That's how we understand the concept. So finding the point of contact, say for example, I have an example problem which says show that 7x plus 6y equal to 13 is a tangent to the parabola y square minus 7x minus 8y plus 14 equal to 0. and hence and find its point of contact. This is how the question reads. So in this case, clearly the parabola given is y squared minus 7x minus 8y plus 14 equal to 0, which on further simplification gives us let me take this as equation 1. Now we have the condition that the line Lx plus my plus n is a tangent to the parabola y square equal to 4ax if n square is equal to ln. So let's initially take this in the standard form. Therefore, equals 7x is what I get, which on further simplification gives me y squared 2 times of 4y, that is 8y. Now this being 4, I add and subtract 4 squared plus 14 equals 7x is what we get. So reducing this in the standard form, I get this as y minus 4 whole square equals 7x minus 16 plus 14 is minus 2, which comes as plus 2 on the right, is what we get. So therefore, this when reduced to the standard form gives y square equals 7 times of this. So as I see here, my 4a is 7, which gives me a equals 7 by 4. And when I have the line 7x plus 6y minus 13 equal to 0, I have this in the form Lx plus my plus n equal to 0, where this is L, this is m, and this is n. So using these 4 basic values, I have the condition for tangency. Now condition for tangency is given by m square a equals nl. This is the formula which we have discussed as the condition for tangency. Therefore, using this, if the left hand side is m square of a, that is 7 by 4, which gives me 36 63, and my right hand side, which is NL, gives me n times as minus 13 times L, which is 7, which gives me minus 91. Now as we can clearly see that my m square a is not equal to NL, therefore 2 is not a tangent to the parabola given by equation 1, is how we conclude, and therefore there exists no point of contact. This is how we conclude the point of contact connected with the tangent. So this condition doesn't satisfy, therefore this line is not a tangent to the parabola, and hence there is no point of contact. The condition for tangency. Now what's the condition for tangency in parametric form is what we're going to discuss here. Suppose I have a parabola y square equals 4ax, and say I have a line which touches the tangent at P of t, and the equation of this line is given by Lx plus my plus n. So I want to see the condition for this line to be a tangent to the parabola y square equal to 4ax. Now clearly we know that equation of tangent at P is given by x minus yt plus at square equal to 0 in the parametric form. We have already discussed this as the formula. Now the equation of tangent is already given to be Lx plus my plus n equal to 0. Now since the parametric form of tangent is this and the equation of tangent given is this, both represent the same tangent. Therefore 1 and 2 represent the same line. Therefore their corresponding coefficients must be in same ratio, that is L by 1 or 1 by L equals minus t by m, and that equals at squared by n is what we get. So from these two I get t equals minus m by L, and from the first and last equation I get at squared is n by L, that implies a times of t squared, which is minus m by L whole square, is n by L, because this is simply substituted with t equal to minus m by L in place of t squared. That gives us am squared is nl, is how I get the two conditions given by am square equals nl. This is condition for tangency. So condition for tangency that the line Lx plus my plus n equal to 0 is a tangent to the parabola y square equal to 4ax is simply am squared must be equal to n times L. Now finding the point of contact, that is the point T, in terms of L, M, N and A. So let's see how we can find the point of contact. Now the point of contact here is P of T is already given as at squared and 2at in the parametric form. But in the previous case we have discussed that t is minus m by L, which we have obtained through the proportion of these two, where L by 1 or 1 by L equals minus t by m. So t is minus m by L, which I get from these two equations. So using the value of t as minus m by L, I just simplify, substituting in the point. So with t equals minus m by L, substituting this in this, we get P of t is at squared, that is a times t squared, and 2a t is what we get. So in place of t, which is substituted here, I get this to be am squared by L squared and minus 2am by L is what we get as the point of contact. So my point of contact of the line Lx plus my plus n to the parabola y squared equal to 4ax is am squared by l squared and minus 2am by l, or this can also simplified to be n by l and minus 2am by l. Both are these points of contacts in their different forms for the parabola y squared equal to 4ax with the line Lx plus my plus n equal to 0, the point of contact of the line with the parabola.